Hello and welcome to another digital design class. In the previous class, we spoke about registers, shift registers, and we ended that part of the registers and flip-flops. And we spoke a little bit about the state diagram. Today, we will continue state assignment and how we can use that state diagram to design a sequential logic circuit or minimize a sequential logic circuit. We will also go through the procedure of designing sequential logic circuits using the state diagram and the truth table, so on. So from the previous class, we learned about the state assignment, and to minimize the cost of a combinational circuit, we had three possible binary state assignments. M states need n bits, where 2 to the power of n is greater than m. This table shows three possible binary state assignments. For example, state A, B, C, D, and E. And assignment number 1 for binary is going to be 0, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0. And we could see the assignment 2, or the gray code, again, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 0. And we can have another assignment as well, assignment number 3 or 1 hot. So any binary assignment is satisfactory as long as each state is assigned a unique number. We usually use the binary assignment number 1, and this table shows the reduced state table with the binary assignment of 1. So if the present state is 0, 0, 0, and x is 0, then the next state would be 0, 0, 0. If x is 1, next state would be 0, 0, 1. And from 0, 0, 1, if x is 0, the next state would be 0, 1, 0, for example. If x is 1, it's going to be 0, 1, 1, and so on. Now, we use these state assignments to be able to design combinational logic circuits. I think it's better to learn this using an example. So the procedure goes like this. The design procedure for sequential circuits. For combinational logic circuit, as you remember, we use the truth table, and then we use the K-map to extract a function, Boolean function from that. And using that Boolean function, we built the combinational logic circuit. For sequential logic circuits, it's the same almost, with small differences. So the word description of the circuit behavior to get a state diagram. Then we would do the state reduction if necessary. Then we would assign the binary values to the states. We would obtain the binary coded state table, choose the type of flip-flops. By the way, this is exactly like combinational logic circuits. Sometimes we can design with either types of flip-flops. For example, in a combinational logic circuit, we learned that we can replace a NOT gate with a NOR gate or a NAND gate when we tie the inputs together. For flip-flops and sequential logic circuits, we can replace a T flip-flop, for example, with a D flip-flop or a JK flip-flop, something like that. And it's up to us. Sometimes in the question, it has mentioned that you have to use this specific type of flip-flop. So we don't have any options. For example, they will give us a state diagram and ask to design it with a JK flip-flop. And sometimes they would simply ask to use a sequential logic circuit to represent a state diagram or a Boolean function. So they will rather give us a state diagram or a truth table. And we have to figure out the design using the truth table or the state diagram. And I'll give you an example for that. Then after choosing the type of flip-flop, we will derive the simplified flip-flop input equations and output equations using the K-map. And finally, we will draw the logic diagram. I think this slideshow would show a great representation of that. 1 second. Okay. Now, as an example, to design a clocked sequential circuit, the first example, we want to detect 3 or more consecutive ones. Now, this is the state diagram that we have. By the way, S means S0 means state 0. We would have, in this particular example, we have S0, S1, and S2, and S3. The state diagram looks like this. So the example will be like this. We want to detect 3 or more consecutive ones, and the state diagram will look like this. Now, the first thing that we need to do is to find the truth table for this. So state S0 means A and B are 0, 0. State S1 means A is 0 and B is 1. State S2 is A is 1 and B is 0. And S3 is 1 and 1. Again, we want to find 3 consecutive ones. So using this state diagram, we will draw a truth table for it. And I want you to help with this. So if, for example, A and B are 0, 0, meaning we have S0. So this is, let me bring up the pen. If it's 0, 0, this is our X. These are our X. So 0, 0, if X is 0, what happens to A and B? It goes back to 0, 0. Okay, and what would our output be? Y. And by the way, this is Y, A, B, and the transitions are X. Okay, so the inputs are X, the outputs are Y. Now, if A and B are 0, 0, and X is 1, what happens? So 0, 0, and X is 1. What would the next state be? By the way, S0 means 0, 0, S1 means 0, 1, S2 means 1, 0, and S3 is 1, 1. Now, if A and B are 0, 0, X is 1, what happens to the next state of A and B? It becomes what? 0, 1, thank you. And what is Y? 0. So it goes 2, 0, 1, and Y is 0. Again, this is 0, 1. Now, if we are at 0, 1, we are at this point, and X is 0. So 0, 1, X is 0. What would the next state of A and B be? 0, 0. Thank you. So 0, 1 gives us 0, 0, and the Y is 0. Now, if the present state is 0 and 1, again, we are at that point that I showed with the flash. If we are at this point and the input X is 1, what happens? We will move to 1 and 0. So we would move to 1 and 0, and Y would be 0. Now, at this point, we are here in the state diagram. S2 is 1, 0. The input is 0. What happens when the input is 0? We do it with a different pen color. So we are at this point, 1, 0. And the input changes to 0. What happens when we are at 1, 0 and x is 0? What is the next state? And what is S0? It's 0, 0. So here we would have 0, 0. And what is y? Y is also 0. Okay. Now, again, we are at 1 and 0, which is S2. We are here. But this time, x is 1. So when x is 1, what is our next state? S3, which is 1, 1. And what is y? Y is what? 1. So we're going to have 0, 0, 0, and 1, 1, 0. Now I want you to think on the last one and tell me what the last one is. So the present state for the last one, we are at this point. I'm going to show it here. We are at 1, 1. What happens if x is 0? What would the next state be? Sorry, what? Tyler? Thank you, 0, 0. And what would the output be? 0. What if we go from 1, 1 with the input of 1? What is the next state? 1, 1, thank you. And what is the output? 1. So 0, 0. Where did we go? And yes, 1, 1, 1. Now, if we want to synthesize using a D flip-flop, by the way, there's a small typo here. This y should be 0. We want to find first, we want to find 3 of the outputs. We want to find A, B, and C, okay? Where do we have 1s in A? We have a 1 here, we have a 1 here, and we have a 1 here. This is 3, this is 5, this is 7. By the way, 0, 1, 2, 3, 4, 5, 6, 7. So the minterms, the sum of products is going to be 1 at 3, 5, and 7. What about B? Where is B1? B is 1 here, it's 1 here, and it's 1 here. So B is 1 at sigma of what? 1, 5, 7. So B is 1 at sigma of 1, 5, 7. And just for now, you know, that error, imagine that we have this truth table for now. And where is Y1? 6, 7. And Y is 1 at 6 and 7. Okay, I would correct this in the final. Now that we have A, B, and C, Y, their minterms, we can draw their K-map and synthesize them using a D flip-flop. So for A, B, X, sigma of 3, 5, 7, when we draw the K-map, this part is going to be BX, and this one is going to be AX. So it's going to be AX plus BX. Now I want you to find the function for B and Y. So B and Y. Again, let me... B was what? We want to find the function for B and Y. So Y was 6 and 7. I don't remember what B was. Do you remember? It was 1. Go. 1, 5, 7. 1, 5, 7. 1, 5, 7. The first student to find these two is going to get extra points on their assignments. I want to find the function for b, or db in other words, and dy, using its sum of products. Now I'll give you 5 minutes to solve these two. Okay, did anyone solve it? Yes. Okay, what is the answer? AX. Okay. AX plus B naught X. Okay. I think that's correct, yes. Thank you. And what is dy? Perfect. Thank you. So remind me to give you the bonus points. Okay. So by drawing the K-map, again, this is 0, 1, 3, 2, 4, 5, 7, and 6. So we would have 1 here at 1, 5, and 7. And combining them and simplifying them, we're going to have here, we're going to have B prime X. And in the bottom one, we're going to have AX. And for 6 and 7, we would have AB. Now, using these three equations, we can build it for the D flip-flop. As you know, the D flip-flop is also called the data flip-flop. It's capable of storing 1 bit of data. So we will directly connect DA, which is AX plus BX, to the input D of the first flip-flop. Again, this is A because it's connected to A. So this one would be AX. And here, this is connected to B, so this is B. And this is BX, so this would be AX plus BX. And for DB, we have this connected to A again, so this is AX. And, oh, I'm sorry. This, again, I'm sorry, this is connected to AX. And down here, I have X connected to B prime because it's, if this is B, this would be B prime. So we have B prime X here as well. So the output of this would be AX plus B prime X. And finally, we have Y, which is AB. So I can get it directly from the output, which is A and B. So this is going to be AB. A. So this is when we want to design using a D flip-flop. If we want to design it using other types of flip-flops, so T flip-flop or JK flip-flop, I'll also mention that as well. So we have designed it using the D flip-flop. Let's see what happens in the excitation tables. When A or QT and QT plus 1 are 0, 0, D would be 0. When it's 0, 1, it's going to be 1. When it's 1, 0, it's going to be 0 to D. And when it's 1, 1, it's going to be equal to 1. And this was for D flip-flop. For the JK flip-flop, going back to the JK flip-flop truth table and excitation table, if the present state is 0 and the next state is 0, then the JK flip-flop, if it's 0, 0, we have no change. If it's 0, 1, we would have reset. If it's 0, 1, then the output JK would be 1, 0, which is toggle, or 1, 1, 1, which is toggle, or 1, 0, which is set. If we have 1, 0 in the present state and next state, the flip-flop output JK would, the JK flip-flop would be 0, 1 would be reset, and 1, 1 would be toggle. And finally, when it's 1, 1, we would have the output of 0, 0, 2 different outputs, or 1, 0, which is no change, or set. So what is the correlation between these two? You can see that the first part, if I have the first row, the J's, it's going to look exactly like the D flip-flop. It's just going to be 0, 1, 0, 1. Now, if we want to use a T flip-flop, the excitation table for a T flip-flop, by the way, T flip-flop is also called the transfer flip-flop as well. So if it's 0, 0, the output would be 0. If it's 0, 1, the output would be 1. If it's 1, 0, the output would be 1. And if it's 1, 1, the output would be also 0. Will be 0. So if the inputs are the same, the output would be 0 for a T flip-flop. If it's different, it's going to be 1. And on a happens. Now, let's design the sequential circuit with a JK flip-flop for the same example. We want to detect 3 or more consecutive Y1s. Now, for a JK flip-flop, using the previous table, if A, the present state, is 0, and the next state is also 0, then JA would be 0, KA would be X. Again, if we go back to that table, I can't put it side by side, but you can go back and look at it on your notes. And if B is 0 and B goes from 0, 0, again, we're going to have 0 and X. Now, if A is 0, A, the next state is also 0. Going from 0 to 0, again, we're going to have 0X. And when we go from 0, which is present state, to 1, then we're going to have 1X. 1 and KB is going to get, because we don't care about that one. Again, going from 0 to 0, we're going to have 0X. Going 1 to 0, we're going to have X1. 0 to 1 is going to be what? Can you help me on this one? I'm going from the present state, which is 0, to the next state, which is 1. I had the same thing here as well. 0 to 1. It's going to be 1X, and going from 1 to 0 gives us X and 1. Again, going from 1 to 0 gives us X and 1. Going from 0 to 0 gives us 0 and X. Going from 1 to 1 gives us X0. Going from 0 to 1 gives us 1X. 1 to 0, again, we know that it's X1, and 1 to 0, X1. 1 to 1, X0, and 1 to 1, X0. Now, exactly like the previous table, we want to find where JA is 1, where JB is 1, where KA is 1, where JB is 1, and so on. So JA is 1 only here, which is 3, 0, 1, 2, 3, 4, 5, 6, 7. So it's 1 here, so it's going to be sigma of 3. And KA, let's find the KJs and Ks. KA is 1, only the 2, which is 4 and 6. JB is 1 and 1, 5. So 1 and 5. And KB is 1 at 2, 3, 4, 6. 2, 3, and 6. Now we want to find DJA, which is A, B, and X. So A, B, and X. We want to find when we have any of them equal to 1. And we have 3 consecutive 1s in them. So DJA X. Just give me 1 second to find it. Yeah. So this is from the flip-flop that we had, the exact flip-flop that we had previously as well, the D flip-flop. I think it's better to go, because half of the information is on the next slide. So I'm going to show you the next slide and I'm going to go from them. So to synthesize this, we want to find JA and KA. JA is going to be equal, again, JA was 3 and KA was 4 and 6. So JA was 3. And by the way, we have to put the don't cares as well. I forgot to mention this part. So JA is equal to sigma of my pen stopped working. So it's going to be the sigma of 3, but the don't care plus the don't care, which was the don't cares for JA is going to be 4, 5, 6. Don't care of 4, 5, 6. I think it was also 7. 4, 5, 6, and 7. So if I draw the K map, it's going to look like this. 0, 1, 3, 2, 4, 5, 6, and 7. And let me change the color. 3 is 1, and all of these are don't care. If I combine them, I can combine this one and this. So when combining them, JA would be equal to BX. And why didn't I combine these together? Don't care, so you don't even need to put it. And by the way, let's go back to one of the questions that you had in the exam, and a lot of students got it wrong. And the question was like this. You had a 1 in the middle, and everything else was an X. Do you remember this question? Yes. You just combine everything together, and F would be equal to 1 for that question. So if everything else was X, I could just put JA as 1. But here I can't, because I can't combine all the don't cares without a 1. Now KA is going to be, again, 4, 5, 6, 4 and 5. 4 is 1, 5 is 0, 7 is 0, and 6 is 1. And 0, 1, 2, 3 are don't cares. And when we combine them, we can combine 0 with 4 and 6 with X, or one of the don't cares. Now JA is going to be BX, and KA is going to be X prime. Now JB and KB, again, for JB, we use the table. I wish I could put both slides together, but when you're studying this at home, make sure that you put the slides together so you would understand where we got these numbers and how we filled the K-map using the truth table. So when we simplify JB, we're going to get X by combining the 4 squares in the middle. And for KB, we can combine the 2 on the sides and the 4 on the top, and we're going to have A prime plus X. Now, when it comes to designing the JK flip-flop, J is going to be equal to BX. So JA, by the way, the J for flip-flop A, and this is flip-flop B, is going to be equal to X, and this is connected to B, so this is going to be B. The output of the AND gate is going to be BX. And for the bottom one, JB is just X. This is X. And now KA for the first one is X prime, so X, and this is X prime. And KB is A prime plus X prime. Now this is connected to A, sorry. It's connected here to A. And this is connected to X. Now, what do I have here at the end of this NAND gate? I have AX bar prime, which is equal to A prime plus X prime, using De Morgan's law. You remember this? So you can build it either way, just using one NAND gates, or you can use two NOT gates and an OR gate. The easy way is just using one NAND gate. Again, this is equal to AX bar. So we designed it, the example using a D flip-flop. We designed it using a JK flip-flop. Now let's use a T flip-flop. Now for a T flip-flop, we have two inputs for the flip-flop, TA and TB. The present state is 0. The next state is 0. And the input is 0. So when we go from 0 to 0, TA would be 0. Again, B, when we go from 0 to 0, TB would also be 0. So present state, we are going from 0. Next state is 0. Therefore, TA is again 0. If I'm going from 0 to 1, TB is going to be equal to 1. Now, I want you to help this one by looking at the previous rows. If I'm going from 0, the present state, to the next state, which is 0, what would TA be? I'm going from 0 to 0, no changes. It's going to be what? 0. Thank you. But where I'm going from 1 to 0, I'm changing the state. It's going to be 1. Thank you. Again, 0 to 1, I'm changing a state. It's going to be 1. 1 to 0 is going to be 1. So 1 and 1. 1 to 0, again, it's going to be 1. 0 to 0, 0. 1 to 1, 1. I'm sorry, 0, because it's no change. And 0 to 1, 1. 1 to 0, there is a change. It's 1. And 1 to 0, again, a change. It's going to be 1. 1 to 1, no change, 0. 1 to 1, no change again, 0. Now, if I want to write the equations for them, we have to extract the minterms. Where is TA1? It's 1 here, and another one here, and here. Again, 0, 1, 0, 1, 2, 3, 4, 5, 6, and 7. So it's going to be sigma of 3, 4, 6, TA. What about TB? Do a different color. TB is going to be equal to 1, 2, 3, 5, and 6. 1, 2, 3, 5, and 6. 1, 2, 3, 5, and 6. Now, I'm going to give you 10 minutes to solve the Boolean function for each of these minterms. And the first person to solve both is going to get extra point on their upcoming final exam. So sigma of 3, 4, 6, and sigma of 1, 2, 3, 5, and 6 for TA and TB. Uh, according to for the in-person class, according to our final exam schedule, your exam is on Thursday, December 11th, I think, at 10:15 a.m. Please double check it, but according to the calendar, it's going to be when the class meets on Tuesdays and Thursdays at 1 p.m., the exam would be 10:15 a.m. Thursday, December 11th. For the online students, I have already posted the exam time and date and instructions. It's going to be this weekend for all the online students. It's going to be this weekend, and they're going to have a window to take the exam. Great. Yeah, I think it's. The exam is going to be a comprehensive. It's going to have everything that you've learned so far. The format is going to be the same as your midterm exams. You're going to have multiple choice questions, and I think you have 1.5 hours to take the exam. And yeah, that's it. Do you want me to? Okay, so to sensitize using the T flip-flops, first one is going to be A x prime plus A prime bx, TA, and TB is going to be A prime B plus B XOR with X. And that's actually B prime X plus X prime B. But you can, simplify it as B XOR with X. Now, to draw the gates for it, the upper one is the A flip-flop, the lower one is the B flip-flop. And for the A flip-flop, we have, by the way, this is X prime and this is A, so it's going to be A X prime. And the lower one is going to be A prime B X. And you can get the A prime from Q bar, which is, again, A prime, and this is A, and this is B, and this is B prime. And the output of this is going to be the TA that we have here, A X prime plus A prime B X. And TB is going to be A prime B plus B XOR with X. Again, we have B and then X, which here we have B XOR with X. And here we would have A prime B. And this would be TB, which is A prime B plus B XOR with X. Okay, that's it for this example. And the course is concluded here. I would recommend that you study this at home step by step. We may gone too fast covering this part. So I would recommend just write it on a paper, go step by step, make sure you understand how we design a sequential logic circuit with a clock, obviously, using a truth table and the state diagram. Sometimes they will provide you with the state diagram. Sometimes it's just the truth table. And the FE exam, I've seen some years they give this type of question, but it's not going to be as complicated as this. It's going to be just a simple, single flip-flop with 2 or 3 inputs, something like that. But it's going to be pretty simple. And sometimes you can just put the numbers, and by try and error, you can figure out what the output and the result is. Thank you so much. And I will see you on the final exam. And in the meantime, if you have any questions, just please stop by my office or email me. Thank you.